In this video, we look in more detail at the Arrhenius equation, which relates the value of a rate constant to both the activation energy and temperature. Svante Arrhenius, who received the 1903 Nobel Prize in Chemistry for his work on dissociation of ionic compounds in aqueous solutions, was also the first to recognize that rates of chemical reactions generally increase exponentially with temperature. The change in rate with changes in temperature is largely associated with a change in the value of the rate constant K. He quantified this observation by what is now known as the Arrhenius equation. K equals A times E raised to the power of minus EA divided by R times T, where E is the base of the natural logarithm with a value of 2.718 to 4 significant figures. EA is the activation energy with units of joules per mole. R is known as the universal gas constant with a value of 8.314 joules per Kelvin per mole. T is the absolute temperature, measured in Kelvin, and the symbol A is called the frequency factor or the pre-exponential factor and is related to the frequency of collisions with the correct orientation. It should also be noted that the frequency factor A is considered a constant and is for the most part independent of temperature. It is typically more useful to express the Arrhenius equation in logarithmic form. Taking the natural logarithm of both sides of this equation gives this version of the Arrhenius equation, which actually has the general form of a straight line equation, where the ln k term is equivalent to the y variable, the 1 on t term is equivalent to the x variable, the negative of the activation energy divided by r, the universal gas constant, is the slope, and the natural log of the frequency factor is the y-intercept. This equation predicts that a plot of ln k versus 1 on t will be a straight line with a slope equal to minus EA on R and a y-intercept of ln A. We can therefore determine the value of the activation energy EA by measuring the rate constant K at several temperatures and then plot the natural log of K versus 1 over the temperature, and then we can calculate the value of EA from the slope of the line that results. So for example, we could measure the value of K for a particular reaction at a series of different temperatures, take the natural log of those K values, and take the inverse or reciprocal of the temperature values, and then plot these values against each other on the graph on the right-hand side, and then find the slope of the line to allow calculation of the activation energy EA. In practice, however, it is generally more convenient to use this version of the Arrhenius equation and measure the rate constant K at just 2 temperatures. If we carry out a reaction at one temperature T1, we can use experimental approaches already seen in previous videos to determine the value of the rate constant K at that temperature. And if we carry out the same reaction at a different temperature T2, we can determine the rate constant at that second temperature, leaving us with 2 different versions of this equation containing rate data from experiments at 2 different temperatures. Rearranging both equations to make ln A the subject of both equations, we can see that the right-hand side of each of these equations are both equal to the natural log of A, and therefore equal to each other. If we rearrange this equation to collect terms, we get this expression here, which can be rearranged to this expression here, where we see that we can calculate the value of the activation energy EA if we have experimental data about the value of the rate constant at one temperature and the value of the rate constant at a second temperature. A much simpler approach than plotting values from many experiments and measuring slopes on graphs.